Good morning, guys. Today we're going to study about discrete logarithm, Diffie-Hellman key exchange, attacks, and Elgamal encryption. So before going to discrete logarithm, hang on. Okay. So discrete logarithm. So before going to discrete logarithm, we need to know about congruence classes. So what do you mean by congruence class? We have studied already in this module 1. Here I'm just briefing it out about congruence classes. So suppose assume x is of any integer and we're going to mod with a p. P can be of any integer. See, for example, what I'm taking is I'm taking 46 as my x value and 12 as my p value. So here I will going to find out the congruence class. How to find out this congruence class? So we're going to divide this number 46 by this 12. So if we divide by this 12, 12 3s are 36 and the remainder is of 10. So that 10 will be my congruence class. So you guys familiar, I guess. So we're going to move on to the next. See, so here 3 be my x value and 17 is by p value. What I will going to do, I will going to check out the generators. So I'm going to talk more about these generators later. So what I will going to do, first I will going to write 3, I will going to the rise to the power 1, 3 power 1 mod 17. 3 power 1 is 3. If we do mod with 17, I will going to get this 3, where I am marking with blue. Okay, so and again I will going to raise this 3 to the power 2, 3 square. So 3 square is 9, 9 mod 17 is 9. My remainder is 9. See, for example, and again I will going to raise the power 3. 3 cube is of 27. 27 mod 17 means 27 divided by 17. 17 ones are 17 and the remainder will be of 10, where it is marking. So likewise, if we are keep on raising 3 to the power of 4, 3 to the power of 5, 3 to the power of 6. For all those things, if I do the mod 17, I will going to get the numbers 1, 2, 3, 4, 5, 6 up to 16 I will going to get. So if I am getting a number with a p minus 1 terms, then that number will be called as generator. See, for example, if I do 3 power 16 mod 17 till that 3 power 1 to 3 power 16, if I do, I will going to get all these numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we do 3 power 16 mod 17, we will going to get the answer as 1. So if we get the 17 minus 1, that is 16, all the 16 numbers, then that number will be called as a generators. If I want to keep that in a definition form, I will going to keep, okay, element of A is called a generator of G when you get all elements of G. See, for example, if I take G is equals to Z6, so Z6 should contain P n minus 1, 6 minus 1 terms, that is 0, 1, 2, 3, 4, 5, up to 5 it contains, then that will be called as generators. Okay, so it is now, it is easy to find out these things. 3 power x can be of any value mod 17. If it is of x value is of 1, 3 power 1 mod 17, which is 3, which is very much easy in order to find out this congruence class. But it is very much difficult in order to find out. See, 3 will be given, mod 17 will be given, and the congruence class 12 will also be given, but we need to find out the x value, raised to the power value. So in order to finding out this raised to the power of value will be called as discrete logarithm. So the answer will be given. We need to find out the log, the raised to the power value. So in order to find out the raised to the power of value is very much difficult. So that finding is called as discrete logarithm. So here 3 power 29 mod 17, which is going to give 12. You can easily calculate using a calculator, which is easy task. But it is very much hard to calculate. The 12 will be given and 17 3 mod 17 will be given, but in here we need to find out this question mark term, which is very much hard. That will be called as discrete logarithm. Hope you guys have understood what do you mean by a discrete logarithm. So next we will going to move on to Diffie-Hellman key exchange. Okay, so what do you mean by Diffie and Hellman? So here, the Diffie and Hellman are the two scientists who invented this Diffie-Hellman key exchange. So here, consider these two parties, A and B, that needs to agree upon shared secret key. So these two are agreed in order to share their secret key. So on widely used method, Diffie-Hellman key exchange, is published in 1970s. At the year 1976, it was published by Diffie and Hellman. As I said, Diffie and Hellman are these two scientists. Okay, so now what are we going to do? For an example, we are going to assume and B A and B are the two parties which are agreed upon to share the secret key. So now the base G, so G will be called as generator and P will be of a modulus P. P will be of prime number or any number. So here what this A will going to do, they will going to participate. So where A chooses a random integer A. So A chooses a random integer A. So A should be such a way that it should be greater than 1 and it should be less than P minus 1 term. So this will going to compute the partial key. So this will going to compute a partial key, that is G par A mod P. So this A is a random integer. So G par A mod P, it will going to compute and it will going to send it to B. So what this B will going to do, B will choose us a random integer B. So B should be such a way that it should be greater than 1 and it should be less than P minus 1 and computes a partial key, that is G par B mod P, and it will going to send back to A. So on the recipient of A's message, B computes G par B mod P with of A's random number. So we're going to multiply this, we're going to get G par AB mod P. So same way at the B's end, on the receipt of B's message, A will going to get compute G par A mod P to the power P. So we are going to multiply A and B, we're going to get GAB mod P. So they will go, so for both will be A and B will be having the secret key GAB mod P. So here B will also be having GAB mod P. So they will going to share this common secret key. So this is what the Diffie-Hellman key exchange is about. So let us solve a problem on this Diffie-Hellman key exchange. So the problem, select my P will be a prime number which is of 131 and G is equal to 2. So let a random number chosen by A be 24. So this 24, I have taken it as a random. You guys can take whichever the number you want. So the partial key is 2 is what the generator G to the power 24, which I have taken it as a random number 24 mod 131, which will going to give an answer as 46. Whereas for the second term B, so let the random number chosen by B is 17. I've taken my random number as 17. What I will going to do, same as of A, 2 raised to the power 17 mod 131 will going to give the congruence modulo 72. So after receiving B's partial key, A computes shared secret key. That is what it is. So 72, which is obtained by a B's partial key, we're going to use it here, and we're going to share the 24, which is a random number which is generated by A, and we're going to do mod with 131, which will going to give congruence class of 13. So after receiving A's partial key, whatever the answer we will get here, so that 46 we're going to use, and the B's random number, which is 17, we're going to use here. We will use here, and we're going to do mod, we're going to get 13. So 13, which will be same in both A and B. This is how we're going to solve a problem. So next we're going to see attacks. So attacks is of only one attack, that is man in the middle attack or Diffie-Hellman key exchange attack. So here in Diffie and Hellman key exchange, what we have taken only A and B. So where A and B will going to share a secret key, but here we are going to use C. C will be acting as an attacker or C will be acting as an intruder. So what A will going to do, A same A chooses a random integer A, where it is, 1 second. So A chooses a random integer A and it will going to compute G par A mod P, where G will be a generator, P will be a prime number. So it will going to compute G par A mod P, which will be sent to B. But what A will going to think, I am sending this to B, but actually it will be receiving by an attacker or the intruder who will be acting as a middleman. So it will be attacked by an attacker, and what this C will going to do, C will going to choose its random number C and it will going to compute G par C mod P and it will going to send it to B. What B thinks, B thinks it has been received from A, but actually it is received, it has been sent by C and that will be received by B. So what B thinks? B thinks that it has been received from A. And what B will going to do? B will going to choose a random number B and it will going to compute G par B mod P and it will going to send back. What B will going to think? B will be thinking that I am sending my message to A, but it's not. It will be sent to an attacker C. So attacker C will be knowing what G's random number and C's random number. So G will going to keep all those number and will going to send back G par C mod P here. So at the time of computation, so what A will going to think, C might be sent from B and it will going to compute and it will going to get G par AC mod P and it will going to send back. And here C, what B will going to think, B will going to compute G par BC mod P, which will be shared in common with C. So C will be having both the secret key G par AC mod P and common secret key G par P mod P. So here what we think, A and B might think that they have a secure channel for communication by encrypting all the messages. Instead, A shares the secret G par AC mod P and mod P with C, and B shares the secret key G par BC mod P with C. So in reality, what it will going to do, this attack is possible because B believed that the partial key G par C mod P that is received from A, and A believed that the partial key G par C mod P that is received from B, they neglected to authenticate the source of partial keys that they have received. So this could be done in order to get the man in the middle attack, where the attacker will going to attack on us. So this is what the man in the middle attack is. So next we're going to see about Elgamal encryption. What do you mean by Elgamal encryption? So there is no much here. So here we're going to solve a problem on this Elgamal encryption, where they will going to give a prime number P which will be equals to 11 and alpha equals to 2. What do you mean by alpha? I'm going to tell you later. And A value is equals to 5 and K equals to 4. X will be my plain text, that is equals to 7. And my public key will be, so see, what do you mean by public key and private key? I'm going to tell, for suppose A will be a sender, B will be a receiver. So B will be a receiver, will be having a public key of 3 terms, which is P, alpha and beta. So this public key will be known all over the world. So that the same thing will be known by A also, and the private key of A. So hence public key is of P, alpha and beta. So alpha value they have given, A value, that is a private key that has been given. So here what we need to find out, we need to find out beta value. So we need to find out beta value. We know P, we know alpha, we need to find out beta. How to find out this beta? Beta is equals to alpha raised to the power A mod P, where alpha equals to 2, 2 power A value is 5 mod 11. If you 2 power 5 is 32, 32 mod 11 will be equal to 10. So now what we need to find out, so as it as an encryption means we need to convert the plain text to a ciphertext. In order to convert the ciphertext, so ciphertext will be converted in this term C equals to y1 comma y2. So for y1 and y2 there are two different formulas. For y1, alpha raised to the power k mod p. For y2, x dot beta raised to the power k mod p, where alpha equals to 2 raised to the power of 4. So alpha value is 2 and k value is 4 and mod 11. P value is 11. So we're going to get an answer as 5. So whereas in order to calculate y2, x dot beta raised to the power k, k value is 4 mod p. So x value is, the plain text is 7, 7 dot 10, beta value what we have got from here is 10. So 10 raised to the power of 4 mod 11 we're going to give it as 7. So here we have got ciphertext, that is y1 and y2. y1 is 5 and y2 is 7. y1 is 5 and y2 is 7. So we need to decrypt. So the encryption done. So encryption means conversion of plain text to a ciphertext. So we have converted a plain text to a ciphertext. Now we need to decrypt. So we need to convert the ciphertext back to a plain text. So we have a formula D equals to y2 into y1 to the power p minus 1 minus a mod p, where y2 what we have got is 7 and y1 what we have got is 5, raised to the power p value is 11 minus 1 minus a value is of 5 5 mod p. So 7 into 5 raised to the power of 5. 11 minus 1 is 10. 10 minus 5 is 5. 5 raised to the power of 5 mod 11. We are going to get my d value equals to 7. This is what we have learned about Elgamal encryption. So thank you.